Hi there, this is our second look at polar curves. We're going to look at the shapes of polar curves. And the last time we did a couple of things. We plotted points. So we learnt three formulas, I think. We learnt that a point can be written as p equals r comma theta. That was the first thing, where r is the distance away from the pole, which you should remember is the middle, and theta is the angle at which it is drawn. You might recall that theta starts here with 0 degrees. And it gets bigger going this way around, or it could be in radians, of course, as well. Now, bearing that in mind, we had three equations from memory. We knew that there was a link between r squared and the Cartesian coordinates x and y. That's just Pythagoras. But we also knew that r was related to, x was related to r cos theta, and that y was equal to r sine theta. So these were quite important equations. But we also started looking at some standard equations. So rather than GCSE and AS level maths or something, you might know that y equals, say, 3x plus 1. You might know that that is a straight line equation. You might know that it passes through the y-intercept at 1. You might know it's got a gradient at 3. So you know certain things about certain relationships, certain equations. Y equals 3x plus 1 is 1. There's others, obviously. Y equals x squared or something like that. You should know the formula and the graph that goes with it. So in polar curves, you get a similar thing. I'm meant to know, for instance, what r equals 2 theta looks like. I'm meant to know, but just from here, you see, I know that's very similar to what it says here. This is r equals theta, and it's got this spiral. So if you type that in to your calculator and got a spiral, you'll probably say, yeah, I think that's right. But there's harder ones as well. And for instance, this cardioid is, notice it might be, for instance, r equals 1 plus. Now notice it says that these two things have to be the same. So let's make that a 2. But it says a over b is equal to 1. That means they're the same. So 2 plus 2 cos theta, for instance, would be a cardioid. Type it into your calculator, see what it looks. But when you've got different numbers, you can get different things, different types of shape. It might be, say, 3 plus 2 cos theta, or r equals 1 plus 4 cos theta. Now, what I'm hoping is that you start to know what these shapes look like as well. Let's have a look at these then. So we don't need to know necessarily the names. The interesting ones, by the way, I see loads of these rose curves. I see loads of these spirals, the cardioid and the circle, and these variations on it. So we spotted last time there's certain problems with the graphical calculator. So if we type in 1 plus 2 cos theta, now we can do this. I'm just going to pause the show, and I'll keep all that. But what I'm going to do is I'm going to go over to a package. Now this package is great. Now this has just got a different one there. I'll just double click that and I'll type in what we wanted. Now what did I want? I wanted r equals 1 plus. Let's just go back and see what it was. It was 2 cos theta. So 2 cos, theta's on. This is a package called autograph. And that looks like that. Now, that's interesting the way it's drawn it. You'll notice this bit. This is the bit that is wrong. The autograph at least has the decency to tell you that this bit is wrong. It says the graph really is this, but be aware that these bits here are the negative values of r that I was telling you about. So sometimes you get negative values of r. If you chuck 1 plus 2 cos theta, there are certain values of r that will give you negative values. The problem is you get this as well. I'm going to type this in slightly. I've got the wrong one here. R equals 1 plus 2 cos. I'm going to type it in. You have it on this one, type in theta, and it knows it. This is the kind of thing you get. I've typed in exactly the same, but this is what you get on your black calculator if you type it in. It doesn't distinguish between the negative bits of the loop and the positive bits of the loop. And there'll be a temptation, if you just relied on your calculator too much, to draw all of that. So just be aware that if you were to draw all of that, you'd lose some marks. So again, that's what the lovely autograph does. Unfortunately, your calculator does what Desmos does. If you type this in, it gives you a solid line around here. And if you was to draw that, you wouldn't get all the marks. What they want you to draw in the exam for this is an appreciation that basically it does this, and it basically looks like that, but I don't want that bit. You draw that, you're going to lose marks. So this is theta, this is r, and that's what they want you to draw. Presumably they might want you to draw, it crosses here, it seems at -1, crosses here at 1. Where's it cross here? 1, 2, 3. You can see it crosses there at 3. So I'm just showing a bit of interest. This, by the way, remember, is called the pole. So that's interesting. And just be aware then that it's because there are negative values. Now, if you're not convinced by this, if I was to draw the graph of y equals 1 plus 2 cos theta, which is kind of what we've done in the past, well, cos 2 theta is just, basically, it's this kind of shape. It does this. And it does this. But I'm moving it up one. This is a transformation 1 up, a translation 1 up. So it just goes up a bit. And what it basically therefore does is there's some values. And they're not so many. But between here and here, there are values for which there are negative values. And I know that. Because my graph shows me that. And it's between these two values. You could solve that. You could work out what values there are. Just be aware that this problem exists. So your calculator is good, but if you was to draw that, as I have done there, you would get no marks. Well, you might get some marks, but you'd certainly lose some marks. What you're meant to do is this. That is what the calculator should show you, but unfortunately it doesn't. Some of the newer ones might, but this particular calculator doesn't. So let's run through then some of the polar curves you're meant to know. I've written r equals k theta, so this might be, for instance, r equals 3 theta, or 5 theta, or 42 theta. Whatever it is, these are spirals, are called Archimedes spirals, starting at the origin, getting bigger and bigger and bigger as they go out. So you can see it starts at the origin. Now we know it's called the pole now. But it starts at that pole and goes around and gets further and further out. And if I allowed it to go further, it would just carry on going. Bigger and bigger and bigger. That's r equals 2 theta. You get some graphs instead, which rather than saying r equals, they say theta equals. This is just really saying theta equals some number. So theta equals 4, theta equals 28. Whatever it says, that's what the angle is. And here is going to give me a straight line, because it's all points on that angle. There's a slight problem in the calculator again. If you're not careful, you might draw this down here. But these are negative values. This is basically, what's this? This says theta equals 1. That's what my graph is. So this basically says my theta is 1. That's my angle. 1 radian. 1 radian is about 57 degrees. So that looks like 57 degrees. Yeah, I'll go with that. But notice it shows the negative values that would also give you a theta equals 1, but in the wrong direction. So again, I don't want to see this. I want to see that bit. A good graph, basically do that. That's it. Let's go through a few more varied ones. Now I've got r equals b cos theta. Now r equals b cos theta might simply be something like r equals 2 cos theta. Or it might be r equals 5 sine theta. So it can be either of these two. And if I do this, it basically, cos always starts on the x-axis as far as I can work out. And sine does something slightly different. It starts on a different axis. This one, I reckon, starts on the y-axis according to this. So r equals cos theta, if you look at this, it's basically a circle. It's just a simple circle. It's got effectively one loop round. It starts there, goes around, boom, done. Thank you very much. That's what it does. Notice it is 1 away because effectively it is 1 cos theta. I don't put the 1 in, but that's why it looks like that. And here's a second one, r equals 3 sine theta. So I think this should be bigger because it goes further away from the pole. So rather than going 1 away, it should go 3 away. Here's what it should look like. And notice also here, notice it has gone 3 away. It's slightly sort of zoomed out, but you get the idea. It has gone 3 away. So it starts there, it seems. But notice when you do it, because it's sine, it doesn't start on this x-axis, it starts over there. Again, you can type this into your calculator, it's not a problem. it's weird. It's not actually got a radius of 3, has it? It's got a radius of 1.5. So it's a circle, but not an obvious circle. And the direction matters, the position matters. Get it right. You've got a calculator, it does it for you. And on these, you won't get a problem. You can just type them in and you'll know they're right. These are slightly different. R equals B cos theta. So a kind of example I have is, and you can't quite see it, it says R equals 2 cos 3 theta. Now this is what it looks like. Notice 2 cos 3 theta. Now 2 is the bit that tells me it goes across to 2. It goes across to 2. Each of those are on that circle, which is 2 away. The cos theta, notice it started on the x-axis, and it's effectively kind of, I think of this as 3 arms, or you might think of it as petals, rose petals almost. Here's another one. This is R equals 3 sine 5 theta. Well, you'll notice both of these, by the way, I chose to use n is odd, and you can see why. That looks a beautiful shape. It hasn't started on the y-axis. That's the first one here. But it's gone 1, 2, 3, 4, 5. It's lovely. R equals 3. Notice it goes 3 away. 1, 2, 3 away. All of them are 3 away. But it's got 5 arms because they're there. But it doesn't always have to be positive, by the way. I could throw a minus in. Minus 2 cos theta. Cos theta would have been a circle over here. The minus flipped over there. So minus sine 3 theta. So again, what's that look like? Well, I would have said, you see, the original one would have started there. That would have been the first one. But it's flipped it. So it's flipped it downward this time. Notice, though, what happens when n is even. This is when we get the negative values. So be warned about negative values. So 3 cos 4 theta. When you draw it on your calculator, it draws 8 arms. Notice how many arms there are. Cos starts here, always starts on the x-axis. So, but notice with 4 theta, it's got to have 4 theta has got to have 4 arms. So therefore, I don't want all those dotty ones drawn. If I wouldn't ask you to draw this, I'd expect you to draw me one, to draw me another, draw me a third, draw me a fourth. That is the correct answer. Not 8 arms. Only positive values of r, that says. And 2 sine 6 theta. Well, the fact that it says 6 theta, I want 6 arms. You see what the calculator does. Look at that, hundreds of them. In fact, there's 12 of them. You get twice as many. So this is the first one that you get with sine. Always seems to, just move it just a little bit round. And I've got 1, 2, 3, 4, 5, 6. It's those 6 arms I want to draw. You can add numbers on, so I've got a plus b cos theta and r. So here's the more complicated. So I've written 2 plus 3 cos theta. So what's it look like? Well, it's like the one I showed you before. It's actually a cardioid, and it's drawn, if you look at it, 2 plus 3 makes 5. Notice it is 5 away at its maximum. And you just need to know that that middle bit isn't really part of it. So don't draw that bit. Here's 1 minus 2 sine theta. Going downwards again, but when you get these inside bits, don't draw them. This is what we need to know. Calculator works really well, but can confuse us if we're not very good at it. Again, 1 plus 2, ignore the minus, 1 plus 2 goes up to 3. And your calculator tells you how far to go. These are called cardioids. Because they look like heart shapes. So a little summary for you there. These are the type I'm suggesting that I want you to learn what they look like. And we then are, let's pause on me here. And we then are going to look at exercise 9A. Now exercise 9A, I've got it in front of me here. It's just got a few things. It asks you to draw individual points. So it's more than just the curves and the equations I want you to be able to do. I want you to be able to play around the points. So questions 1 and 2 on page 201 are like that. And then it starts wanting you to draw tables and stuff. Now I don't want that necessarily. I want you to be able to sketch the curves. So use your calculator. So for question 3 it says use it and draw a table and sketch a curve. Just sketch a curve. Use your calculator. Sometimes you get asked to shade regions, and that's question 4, and then 5 and 6 is just a mixture of all of it. So have a look at that for me and see what you think, and we'll do the questions in class. Best of luck.